Hello everyone. In this lecture, we will study a theorem called as Fubinis theorem. So, before proving this theorem, I need a few results of calculus of one variable and some definition of double integration to prove this. So, let me recall those results before proving this result. So, the first result is mean value theorem. Of integration. So if you remember, the mean value theorem says that if we have let f comma g are r integrable function on closed interval a comma b such that g is throughout either it is non-negative or non-positive throughout closed interval a comma b such that g is either non-negative or non-positive throughout close interval a comma b, and if small m and capital M are infimum and supremum of f on close interval a comma b, then there exists k belongs to small m comma capital M such that integration a to b f into g is equal to k times integral a to b g. Right, this theorem we have seen. Now further, if f is continuous, then this theorem can be written in a more better way. It says that integral a to b f into g is nothing but, instead of k, we will say f at c integration a to b times g. Now why is this so? Because since f is a continuous by intermediate value property, it will definitely take a value. Now where does c belongs? Where, let me write down that, where c belongs to closed interval a comma b. So if f is continuous, then definitely there exists a c such that k is basically now my f at c. So that is not difficult to visualize. And I also wanted to tell you here, if I take g as 1 in this, because g is non-negative, then you can see that if since g is non-negative throughout a comma b, then this what I have colored one, this equality becomes integration a to b f. If g is equal to 1, then it is integral a to b f is equal to f at c times b minus a. Right. So that is also one version of intermediate mean value theorem if f is continuous and all. Right. So let me have one more prerequisites, that is uh, your Riemann sum. So the Riemann sum for two variable we have defined. I don't know whether we have defined for one variable. If we have defined, then fine. If not, let me define here. So let f is from q, which is equal to a comma b cross c comma d to r real number. Maybe in last lecture, instead of this q, I used r, but now I'm not using r since this real, of course, that r and this real number r was different, but anyway, so this q won't be it's a good symbol. So q is a rectangle, that is a comma b cross c comma d. Suppose it is so be a bounded function, and p is partition of q. Now how the partition of p looks, if you remember in a previous lecture, we have shown this p is basically, you recall this p is basically your p1 cross p2, and now what is p1? p1 is basically a partition of closed interval a comma b, and p2 is a partition of c comma d, and then we had defined that p, right? Then your upper Riemann sum, then Riemann sum is denoted by SPF, which is equal to, is denoted by SEF and defined as SPF is equal to summation. There were two summation, I goes from 1 to n, j goes from 1 to m, f at ui comma vj xi minus 1 xi minus 1 into yj minus 1 bracket complete. Now what is this ui and vj? They were tagged, so where ui belongs to your xi minus 1 comma xi, and vj is a tag on the yj minus 1 comma yj. Right. This was a Riemann sum, and if f is r integrable, then the limit as norm p1 goes to 0, norm p2 goes to 0, then SPF is basically your UF or LF. Right, so let me write down that also. So if f is r integrable, then limit as norm p1 goes to 0, norm p2 goes to 0, SPF is equal to your integration, double integral over q f, right? So which is same as your uf, which is same as your lf. Well, so this Riemann sum, and what else I have done now? Your Fubinis theorem. Our target is to prove Fubinis theorem in this lecture. So Riemann sum and mean value theorem we have done. Now let me go to the Fubinis theorem proof now. So let me write down the statement of Fubinis theorem. So it says as follows. So if we have a function f defined over a rectangle Q which is equal to a comma b cross c comma d to r is continuous function, then a double integral over Q f of x comma y dA. So let me use this. This is double integral symbol. It is same as your iterated integral. So what is iterated integral? A to b c to d f of x comma y. Now here order is dy dx is same as your c to d a to b f dy dx. Dy dx, it won't be dy dx, here it should be dx dy. Let me correct that. So it should be dx dy. So Fubinis theorem basically says that over the rectangle you can swap the limit, right? So this integral is called as a iterated integral, right? So we want to prove this theorem. How will I prove? Proving this is equivalent to saying that what I will do, I will prove that this double integral is same as with this, and similarly I'll prove that this double integral is also same as this, and from so this is 1 and this is 2, and from 1 and 2 I can say that all three are equal, right? So this first term I will try to show equal to this second term. Similarly, first term I try to show that it is equal to third term, implies that first term, second term and third term all three are equal. So if I could able to prove this, then the Fubinis theorem is proved. So proof is not difficult. It needs your Lagrange mean value theorem of integration and Riemann sum definition. So proof. So it's given that f from Q to R, let me write down Q explicitly because I may need it later on. So Q which is equal to A comma B cross C comma D to R is continuous. So f is continuous in two variables. So this means if I fix a variable x from closed interval a comma b, then f of x comma y is a function of y only, because if I fix x, if it is continuous with respect to x and y, then it will be continuous with respect to y for a fixed x. Similarly, in other way, if I fix y, then it is continuous in variable x. So let me write down that. So this would imply f of x comma y is continuous on closed interval c comma d if I fix x. That means for every x belongs to a comma b, and f of x comma y is continuous on a comma b for every y belongs to c comma d, right? Let me call this full part as 1. So continuity in terms of x and in terms of y, this I call it as 1. So since in the previous we have written that f is continuous on C to D, this says that f is continuous on C to D. So if it is continuous, then Riemann theory says that it is going to be R integrable. So this would imply f of x comma y is R integrable on C comma D for every x belongs to close interval a comma b. If it is R integrable, then we can define the integration of it. So over C to D, f of x comma y. Now we, since C to D is a y variable, so we are integrating with respect to y. Now you realize that if I calculate this integration, then this integration will replace my y with constant, means the y will disappear after integrating this. So integration of this will be in terms of x and some constant, right? So maybe a not constant means if f involved the constant, that's fine. So integration of this function is a is again a function which do not have any y, so it will be exclusively a function of x only. So let me call that function as g of x, right? Now what I will do, so this g of x, now I will now define my partition of a comma b and c comma d. So first we have a partition of c comma d. So c comma d we will use the symbol p2. So let p2 is equal to, p2 is a partition from c to d. So c, which is equal to y naught comma y1 comma y2 comma dot 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 ym equal to d, be any partition of close interval c comma d. So if it is partition from c comma d, so you can see that this integration between c to d, there are y0, y1, y2, ym points. So this integration I can break out. Writing this integration is equivalent to saying that c to d, I can say that it is same as, instead of c I will say y0 to y1, then y1 to y2, then y2 to y3, so on and so forth, ym minus 1 to ym, and ym is itself is a d. So that's a rule of, or that's a property of integration. If f is integrable from a to b, and if c is any point between a to b, then you can say f is integrable from a to c and c to b. That is one of the nice property of integration. So that would imply, we can say that integral c to d f of x comma y dy, this can be written as integration. So c is same as my y naught to y1. I can add y1 now plus y1 to y2 f plus dot 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 ym minus 1 to ym, that f. right? So of course, see, f with dy is there. F is a function of x comma y along with dy. That I am not writing. So maybe I am compact while means I will avoid writing more and more notations now. So this is same as, you can see that this is same as summation yj minus 1 to yj of f of x comma y dy, this addition where j goes from 1 to m. If you expand this, you will get the above equations. You can easily check. When j is equal to 1, you will get y0 to y1, plus when j is equal to 2, you will get y1 to y2, so on and so forth. Right. So this is what my integration c to d f of x comma y dy looks. Now what I'll do in this expression, here I will put that value. So integration c, so g of x will be now, instead of this c to d, I'll write this form. So did I mention this? Let me check this. Okay, so this would imply my g of x will look like as follows. So g of x is integration c to d f of x comma y dy, but integration c to d f of x comma y is same as summation j goes from 1 to m yj minus 1 yj minus 1 to yj f of x comma y dy. Now I'll be using a mean value theorem on this. Since my f is continuous and my f is R integrable, so along with this f, I will assume there is a g function and g is to be 1. So by mean value theorem, I can say there exists some, say, vj belongs to yj minus 1 to yj such that now this integration yj minus 1 to yj of f of x comma y dy. Now see, I am assuming that x is fixed, so this is a function of only y. So like mean value theorem, we are using for one variable only. So this is same as f at x comma vj, and my g function is 1 here, so it is yj. So let me write down this into yj minus yj minus 1, and let me call this as uh, well, so this is what I have defined. This I'll be substituting in above equation. So well, so this would imply, so if I this blue color cloud which I have drawn, so if you want you can check out the mean value theorem. So maybe let me you can see that mean value theorem in lecture itself I have defined. See, you can see that g is 1 and f at c, so instead of f that f is continuous, therefore we say f at x comma vj over there, right? So where does c belong? C here was a to b, now our vj belongs to yj minus 1 comma yj, and g is 1, so if it is 1 then it is b minus a there. So in our function it was very clear, we had taken g as 1, so if I compare this with that form, then you can easily generalize this. Now this blue cloud what I have drawn, that I will write it over here. So if I write that, then how does my g looks? Uh, my g of x will look like as follows. Let me check how it was. So summation j goes from 1 to 1. Summation j goes from 1 to m, and now that is f at x comma vj into yj minus 1. Let's number this as, I think I have numbered not so far, I have only numbered 1, so let me number this as 2. Right. Now from 1, let me go for 1 now. Where is my 1? Yeah, this is where my 1 is. So it says that f is continuous on closed interval c comma d for every x belongs to a comma b. Similarly, f of x comma y is continuous on closed intervals a comma b for every y belongs to c comma d. So this continuity I'll be using. So from 1, I can say that f of 1, f of x comma y is R integrable since it is continuous. So it is R integrable on A to B. Similarly, it is R integrable on C to D. So it is R integrable on close interval A comma B for every Y belongs to C comma D. Right. So now let me define another partition. Let P1 is equal to x naught, which is equal to A, x1, x2, dot xn, which is equal to b, be any partition of closed interval a comma b. So then also now I can talk about my g of x. My g of x is continuous. You can see it is continuous on, since g of x is defined on closed interval a comma b, because x belongs to closed interval a comma b. Because f is continuous, so g of x is continuous. Also g of x is continuous on closed interval a comma b. So if it is continuous, implies it is R integrable. So my target is to show that, what is my target? Let us come to the target. Yeah, target is to show that these three integrations are same. So what I will do, I will start with the second one and I will show that second and 1 are same, and then I will start with the third and I will show that third and 1 are same. Okay, so now let's start with the consider integration a to b integration c to d f of x comma y dy dx, which is same as, now I know what is this part is basically my g of x from the definition itself, because we have defined g of x is like this only. But I know g of x is continuous implies it is R integrable. So I can use the definition of Riemann sum on g of x. So what it says that this is same as limit as norm p1 goes to 0 g of ui. I should take summation that I have forgotten to take. Let me take out the summation here. So, summation I goes from 1 to n g at ui xi minus 1. Have I taken summation while defining Riemann sum? Let me check out this. Third, yeah, I have taken summation. Yeah, that's fine. So I was here. Okay. So what is g of ui? That's important. So we can see what is g of ui. This is same as somewhere I have written. G of x is this. So g of ui will be j goes from 1 to m. F at ui comma vj yj minus 1. So let me write down that g of ui, which is same as limit norm p1 goes to 0. G of ui is f of, again I need to take the summation. So summation I goes from 1 to n, summation j goes from 1 to m, f of ui comma vj, then here xi minus 1 into yj minus 1. Now by the way, I have not mentioned where does ui belongs. Here note where your ui belongs to xi minus 1 comma xi. Similarly, yj belongs to yj minus 1 comma yj. Now what is this? If you observe, this is a Riemann sum of your function. So this is same as. So what I got is a to b, c to d, f of x comma y is equal to limit as norm p1 goes to 0 as pf. And now maybe you can say this is double integration, but norm p2 goes to 0 is not given. But you can take norm p2 goes to 0 on both sides, because anyway this RHS is a left hand side is a fixed number. So here it should be dA. Norm p2 also goes to 0. So this is SPF. I should not say dA, it has a specific limit, so that is very important. So it is dy dx, and now this is basically double integral over q f of x comma y dA by definition of double integration. So we have proved that the second and first is same. On similar line, one can prove that. Similarly, one can prove that integration c to d, integration a to b, f of x comma y dx dy is same as double integral over q f. Hence, we can say that double integral over q f is same as the iterated integral c to d a to b f dx dy, which is same as a to b c to d f dy dx, which completes the Fubinis theorem. Thank you.